Oh, I guess it automatically starts. Okay, good morning. So welcome to Rose's Unit 2 for 2021. We're going to wait about 1 more minute just to give people a few more seconds to trickle in, and then we'll go ahead and get started. While we're waiting, I do want to acknowledge that Rose's 2021 has been supported by a number of organizations, and we're very grateful for both their financial and in-kind support. So thank you to the University of Alaska Satellite Facility, the IRIS, the Incorporated Research Institutions for Seismology, the Seismological Society of America, and the seismology section of the American Geophysical Union. Rose's would not be possible this summer without all of their help, and we're very grateful for that. And I'd also like to acknowledge that we have a great team of folks who are helping run this on the back end on their volunteer time, from both our instructors to our cohort of graduate students who are helping with a lot of the organization and technical support. So thank you all. We really appreciate that. So I think let's go ahead and get started. And today, Sydney Diving, who's part of the organizing team, is going to go ahead and introduce our panelists for today.
Today, I'm happy to introduce everyone to my friend and colleague, Tara Nye, who will be talking to us about how to generate synthetic earthquake ruptures and waveforms using a set of codes called FakeQuakes. Tara is originally from Social Circle, Georgia, and graduated from Brigham Young University with a Bachelor in Science in Geological Sciences and a minor in Physics. We met as IRIS interns in 2018, where she worked at the U.S. Geological Survey in Golden, Colorado, to evaluate models for predicting duration-related parameters of strong ground motion for use in ShakeMap. She is currently a PhD candidate in the Department of Earth Sciences at the University of Oregon, where she worked with Professor Valerie Sahakian on earthquake and tsunami modeling and analysis of ground motion models. So go ahead and take it away, Tara.
And one last second before we begin, just a reminder that we do have the Q&A box. So while she's lecturing, feel free to direct any questions into the Q&A box, and myself or one of the other panelists will verbally ask these questions to Tara at a natural pause. So ask away, and we're excited to get started.
Awesome, thank you. Let me go ahead and get this lecture pulled up for you guys. Are you guys seeing the right thing? Not the presenter notes, okay. I always like to take that. Great. So, as Sydney said, my name is Tara, and I'm going to be going over how to generate synthetic data, specifically using FakeQuakes. FakeQuakes is this set of semi-stochastic forward modeling codes that were developed by Diego Melgar. Diego is a professor at the University of Oregon, where I'm a student, and this is something that he actually started working on several years back during his postdoc, I think, at Berkeley. And over the past few years, he has been working on improving and expanding the functions of FakeQuakes. And over the past 2 years, I've been able to work pretty closely with him as I've been using FakeQuakes in my own research. And so I've gotten pretty familiar with some of the intricacies of the code, and I'm excited to be able to share this with you guys and help you learn how to generate synthetic data if that's something you want to do for your own research. So before actually going into FakeQuakes itself, I wanted to give some motivation for why you would even want to generate synthetic data. So synthetic data are useful for predicting ground motion where data are limited. Modern seismic instrumentation has been around for several decades, and many instruments are still constantly being installed. But despite this, there are still regions around the world where we do lack instruments to be able to record data. There are also regions where we do have seismic instruments, but there just isn't a lot of seismic activity. For example, the Cascadia subduction zone, which is located in the Pacific Northwest, is expecting what we call the big one. It's this really large magnitude 9 earthquake. And so we have this large impending seismic hazard, but we don't have a lot of smaller or moderate earthquakes, which is unusual for a tectonic or an active tectonic region. And so because we don't have a lot of smaller recordings, it's difficult to get an idea of the seismic hazards in the region. So synthetic data are really useful, especially in this type of scenario, to be able to further constrain those seismic hazards or to be able to understand how that subsurface geology would actually influence ground motion in a really large earthquake scenario. Synthetic data are also useful for training machine learning algorithms. This is especially the case in earthquake early warning. Machine learning algorithms require crazy large amounts of data, and we have a lot of data for smaller events, but in an earthquake early warning scenario, or like on a big scale or economic standpoint, we care more about the larger events. So maybe a magnitude 7, 8, or 9, something that would cause substantial damage. And for these types of earthquakes, we don't have as many recordings.
Hey, Tara.
Yeah.
There's comments in the chat saying that your slides aren't changing.
Oh, okay. That's fun. Let's see. Sometimes it happens and I don't know why. All right, what are you guys seeing? Are you still seeing the main screen?
Yeah, the title slide.
Okay. Hold on 1 second. I feel like this happened during my comprehensive exams as well. And we'll see if I play it again, if maybe that changes things. Can you guys see when I change it now? Is it doing anything?
No, it still looks the same. I think maybe you might have to stop sharing and then reshare again.
Sorry about that, you guys. 1 second. Can you see when I change the slides?
Yep, it's working now.
Okay, if it does stop, sometimes randomly it will just decide to stop moving. So if that's the case, definitely interrupt me. I'll fix that. Thank you. Luckily, we only went through 1 slide, so we're good. Synthetic data are really useful for machine learning, early warning applications. There is this algorithm that is currently being developed called the M-large algorithm. This is used to sort of estimate different parameters or the size of an earthquake before the rupture completes. And this is specifically designed for larger earthquakes, so like a magnitude 8+, which we don't have a lot of recordings for. And so this algorithm specifically has been using data from FakeQuakes to be able to help train this algorithm. And using all the synthetic data, they've been able to train this algorithm. And this is just an example rupture scenario that they have. And these over here on the right are the different parameters that they're trying to estimate values for. And you can see here that over the duration of the rupture, within about the first 100 seconds, the magnitude is able to stabilize and get a pretty accurate estimate of the magnitude. So yeah, synthetic data are really useful in this type of application. They are also really useful in studies of other rare events. So for example, tsunami earthquakes. This is where my research comes in. And tsunami earthquakes are these rare events that generate tsunamis much larger than you'd expect for their magnitude. So these are usually magnitude 7 or 8, but the size of their tsunami would be comparable to a tsunami generated by a magnitude 9 earthquake. There are only maybe a dozen of these that we even know of that have occurred. Only a couple of these have even been recorded on seismic instruments. So there's very little that we understand about these earthquakes. And so I've been using FakeQuakes to generate synthetic data to, in a way, sort of recreate one of those tsunami earthquake scenarios. So I generate the data and I vary the rupture parameters to get an understanding of how those rupture parameters influence the data. And this is just a figure from some of the research I've been doing, where I've been generating data for the 2010 Mentawai tsunami earthquake, and the synthetic waveforms that I've created are in orange, and I've just compared those with some of the observed ones for certain stations, shown here in black. So basically, synthetic data are a way to fill in the gaps where we are lacking true seismic recordings. I also kind of wanted to go over just a couple other methods that have been used for generating synthetic data. Some early versions of generating synthetic data used what we call a stochastic high-frequency simulation method. This combines functional descriptions of the ground motion's amplitude spectrum with a random phase spectrum. So they have this mathematical way of making this amplitude spectrum for an earthquake, for example, shown here on the right, where they have an amplitude spectrum for a magnitude 5 event and one for magnitude 7. And then they assume that the radiated energy from this spectrum can then be distributed over a duration, which would be equal to the inverse of the corner frequency. The corner frequency is this part of the spectrum where it starts to increase and then flatten. And so basically using the spectrum, this energy is distributed over a duration, which is the waveform. A really well-known version of this is the Bohr 2003 paper. And so they have this functional form of their model where the y parameter over here on the left would be the amplitude spectrum that they're trying to create, which would be a function of that seismic moment of the earthquake, the distance away, and the frequency. And then they create this amplitude spectrum using different components of the ground motion. So they have a source component based mainly on the magnitude of the earthquake. They also have this path contribution because as waves radiate away, they start to attenuate. And so there's this attenuation in the path. There's also a site contribution. The subsurface geology or conditions in a site can really influence the ground motion that you see. For example, if you're in a basin, you could have a lot of basin amplification effects. And there's also attenuation that you would see in the energy at a site if you have a lot of fine scale heterogeneities. And so the site contribution can help produce the attenuation part of this amplitude spectrum. And then finally, they have this other component, which is just for the data type. So whether they're trying to generate displacement, acceleration, or velocity. And this is specifically for high frequency. So this will generate high frequency waveforms, which was useful from an engineering standpoint, where they were focusing more on just high frequency ground motion. We also have this other type of model called the SKEC broadband platform. This is a lot fancier. So instead of generating just waveforms, this generates kinematic rupture models and the waveforms that would go along with it. So instead of just saying, I have a magnitude 9 earthquake, what would the waveform look like? You actually have the rupture scenario and how the slip evolved. And you would have your waveform designed specifically for that rupture scenario, which is really cool. And this type of model doesn't generate just high frequencies, it generates full broadband waveforms. This is also pretty well known, and there have been several different papers doing validation studies on this model, showing how it can be used in different applications. But despite this, there are some limitations to this method. One is that it doesn't really allow for curved faults, which is okay if you're dealing with a small, pretty simple rectangular fault model. But if you're dealing with larger, more complex fault geometry, this doesn't really account for that, and you can't really have a complex fault. It's also limited to distances around 500 kilometers. So if you're wanting to do more of a far field study, this wouldn't really suit your needs. They also don't model P waves here, which is okay if you're focused more on just the amplitude of the ground motion. But if you're wanting to use the synthetic data for an early warning application, those P waves are pretty crucial. And finally, this is limited just to acceleration data rather than other types of data. FakeQuakes is actually really similar to the SKEC broadband platform. It uses a lot of the same methodology, but it's mainly just sort of an improvement against the SKEC broadband platform. So it also generates these kinematic rupture models and the associated broadband waveforms. However, it does allow for curved faults. So for example, here in Cascadia, so this has been really useful as Cascadia is not just a really small, simple rectangular fault. It's this really, really large extending subduction zone, which has a lot of more complex geometry. It also allows for larger distances. FakeQuakes models P waves, which is why synthetic data generated using FakeQuakes has been really useful in developing those early warning algorithms. And it generates displacement data as well as acceleration data. And this is also really useful because high rate GNSS stations, which are a type of GPS station, produce displacement waveforms. And GNSS data has been shown over the past few years to be really useful companion data to seismic data. If you're familiar, or if you've heard about it, seismic data tend to saturate at larger magnitudes, so it can be difficult to tell the difference between maybe a magnitude 8 and a 9 earthquake, but GNSS data don't saturate in the same way. And so it's useful to use both types of data together, which is why FakeQuakes is really useful, because we can generate synthetic data for both the GNSS and the seismic stations. FakeQuakes has sort of three main components to it. The first is generating rupture models, which uses methodology from this Mayan Baroza paper. Then it generates low frequency waveforms. This uses the frequency waveform, or FK, integration code from the Xu and Rivera paper. And finally, it creates high frequency waveforms using methodology from Graves and Patarka. And then it just combines the low and high frequencies together, which give us those final broadband waveforms. Before you start generating data, you want to ask yourself a few initial questions. First is, what type of earthquake are you wanting to generate? Do you want a thrust earthquake, a normal, or a strike slip? This is a type of parameter you can define when you're setting up your parameter file. Another question is, what is the magnitude earthquake that you're wanting to generate? Or are you wanting to generate a whole range or a span of magnitudes? Next is, where is the source region? Where are you wanting to actually generate this earthquake? And with that, what is the regional velocity structure? One of the files that you need to start generating data is a velocity model, because a velocity model is what is used to be able to generate these waveforms. You also want to know what type of data you're wanting to generate. Do you want to generate just displacement waveforms for those GNSS stations, or are you wanting to generate broadband waveforms for acceleration? And finally, what stations are you wanting to use? Another file that you'll need is a station file, which includes all of your stations, as well as some information on the stations and the site conditions. I'm going to quickly go over what these input files look like that you would need. One is a fault model. And the fault model is basically what I consider this large skeletal framework that you're working with. So you have this large fault with lots of subfaults, but when you generate your rupture scenarios, you're only going to be rupturing parts of that fault, not the entire thing. And so this would be an example fault model where the first couple columns are related to the location of all of your subfaults. So you have your subfault numbers, the longitude, the latitude, and the depth. Then you have the orientation of all of your subfaults, the strike and the dip. If you're dealing with a simple rectangular fault model, odds are your strike and dip are all going to be the same. But if you have more complex fault geometry, then these could vary depending on your subfault. The next two columns are kind of dummy columns. They don't actually do anything, but they're left over in the structure of this file from when this code has been used for slip inversions and other things. And so these columns just need to exist for the structure of the file, but the values don't matter at all. And then finally, you have the last two columns, which are the dimensions of your subfaults. So you have your length and your width. If you're dealing with a 2D fault model, those subfaults are squares. But if you're doing a 3D fault model, those would be triangles.
Hey, Tara, we have a question in the Q&A.
Yeah.
Someone is curious to know whether FakeQuakes works for simulating explosions and collapse earthquakes.
That is a good question. I don't believe it's been used yet in that type of situation. Trying to think. I'm not sure if that would quite work at the moment. Trying to think how that would work. I feel like one of our faculty members here actually asked a similar question for his research, and I don't remember what Diego said, but I think this type of model wouldn't work quite as well for that scenario. But that's something I think that we could direct to Diego. If you did actually want to learn more about that, we could ask him. but at the moment, I don't think that it's been used in that type of application yet. But it's always being improved, so maybe we could allow for that. Yeah, for the next file that we need is our velocity model, which I mentioned before. FakeQuakes just uses a simple 1D velocity model. So you have the thickness of each layer. The thickness of the last layer needs to be 0 because after that, it's just assumed to be infinite. The next couple columns are just the velocity. So you have your shear wave velocity and your P wave velocity in each layer. And you have the density of each layer. And then finally, the attenuation, the S wave attenuation and the P wave. And this is in the form of Q, which is this quality factor. If not familiar with Q, basically it describes the amount of energy that is transferred each cycle. So if you have a high value of Q, a lot of energy is being transferred, and so it's not being attenuated. But if you have a low value of Q, you're losing a lot of that energy due to attenuation. And finally, the last file that we need is this station file. Our first several columns list the station name, as well as the longitude and latitude. And then we have these other couple columns, which are the data type. So they refer to these column headers up here on the top. Most of these aren't really used. They're also left over from different applications of code within the MudPy repository. So really all we would want is the second column, which refers to the displacement waveforms. And so the ones fill this column and everything else is zeros because we don't really need to deal with that. And finally, we have our last column, which I believe is optional. It's for this parameter called kappa. Kappa is this thing that describes the slope of the decay of high frequencies. And FakeQuakes can use just a default value, but for some reason, if you do have very specific kappa values for each of your stations, you can include this in your station file.
We have another question in the chat, Tara.
Yep.
Someone asks whether you can incorporate the effects of topography on the simulated ground motions using FakeQuakes.
As in, like topography on the fault or on the surface?
I assume on the surface.
I don't think that that is currently something that is built into FakeQuakes. Sorry, I'm trying to think just for a second if that shows up anywhere that I've seen. I don't think complex topography is really included. Kind of in a way, things are included, such as site conditions or yeah, I don't think it is, because mainly our waveforms are created using, well, we'll go into it, but using Green's functions or using things that we know, such as like the velocity and the rigidity, things like that, the different layers, or what we know about the length of the path the waves are traveling or site conditions. But other than that, like the actual spatially varying topography, I don't think that's included. And I think someone else.
Yeah, we have a couple more questions popping up. So can you simulate active source earthquake data?
I don't think so.
Yeah. Okay. And then the other is there a way to model an earthquake scenario by incorporating moment tensor information?
Well, these are really great questions. To think about the last one. Okay, can you model an earthquake by incorporating moment tensor information? Truthfully, I don't really work with moment tensors much, so I don't know. I mean, if you're able, using the moment tensor, if you're able to then create a fault model from that, I don't think so. You would need to have, basically you need these three files. You need that fault model, you need a velocity model, and you need your station file. If you can somehow create that using your moment tensor, then maybe. but I don't think it's currently been used in that way. Yeah. Cool. And then let me know if any other questions pop up that I don't see. Yeah, so now that we have gone over our files, we can go over how to actually start generating our data and like what's going on behind the scenes in the code. So the first step is actually generating our Rupture models. We start out with that fault model, which is our large entire framework, but then we need to determine the dimensions of the fault that we're actually rupturing for this individual scenario. The dimensions of the fault that we're rupturing are they depend on the target magnitude that you want and these rupture dimension scaling laws. The scaling laws come from this Blazer et al. Paper, and they're shown here. So the length and the width of your subfault are dependent on that magnitude that you set, or the magnitude that you define in your parameters. However, in the real world, not every single magnitude 8 is going to look the same. Some are going to be long and skinny, and some might be short and fat. And so FakeQuakes uses this stochastic approach to the scaling laws to be able to add some of that more real life variability to the rupture scenarios. And so we have this equation here where the dimensions have these coefficients, this A and B, which come from this normal distribution. So instead of having set coefficients in these scaling laws, they come from this normal distribution, which just gives that variability in the size and dimensions of the rupture, but they still produce the same magnitude earthquake that you would want. Once you have your fault dimensions, you want to know the slip pattern that you're going to generate. The first step in this is determining your hypocenter. So where is the rupture actually starting? This can be random, or you can specify a hypocenter. Usually, if you're just generating random rupture models, your hypocenter will be random, but some people do use this in an application where they're trying to recreate a certain earthquake scenario, which is what I do. And so I specify the hypocenter that I know is a hypocenter in my earthquake. Next, after you have your hypocenter, you need to determine the slip that is on each of the subfaults. The slip on each subfault comes from this normal distribution, which is a function of this mean slip value and a covariance matrix. So the mean slip, or the slip, comes from this probability density function where we have this mean slip value. And this mean slip is the amount of slip it would take to produce the magnitude earthquake that we want using those fault dimensions that we just got. So if you're familiar with the equation for the seismic moment of an earthquake, it's a function of the rigidity and the fault dimensions and the amount of slip. We can rearrange this equation so that our slip is a function of our seismic moment, which comes from the target magnitude, and our fault dimensions. Our covariance matrix is what we use to correlate subfaults with each other. So it's a function of the standard deviation of the slip and the correlation between every ith and jth subfault pair. FakeQuakes specifically uses the von Karman correlation function, but there are several different correlation functions, which I have shown here on the right, where these are the spatial random fields for a couple different correlation functions. Mathematically, this is what the correlation function looks like. It's a function of this R parameter, which is some type of distance measure, which I will explain a little bit further on the next slide. But I do want to focus on this G sub H term, which I expanded out. Here, this distance measure is raised to this H exponent, which we call the Hurst exponent. If we take these correlation functions in the spatial domain and we transform them into this wave number domain, this is what they would look like. And this Hurst exponent describes the steepness of the decay of these correlation functions in the wave number domain. So for example, the Gaussian correlation function is represented by all of these circles, and this has a steeper decay than the other correlation functions, which means it lacks more of the higher wave number material, which would be more of the fine scale features. So if we're looking over here in the spatial domain, the Gaussian function shows kind of these large disparities, but you don't see a lot of that fine scale meshy stuff in between. But these other correlation functions have a less steep decay, so they have more of that higher wave number material, and you can see a lot more of the fine scale resolution. This case of H parameter or term is what we call the modified Bessel function of the second kind. If you're interested in what it is, it's basically just the solution to the Bessel differential equation, which is used in solving the 3D wave equation. So again, this is our von-Karman correlation function, and I want to focus on this R parameter, which is a distance measure. It is a function of this strike slip distance and dip slip distance between each of the subfaults and these correlation lengths. So if we're looking here at a fault, this star highlights the central subfault. And so if we're looking at just the central subfault, this panel illustrates the distance along strike for each subfault away from the central one. So for example, these subfaults further away along strike have a larger distance, whereas this panel shows the distance along dip. So all of these subfaults in the upper and lower parts of the fault are further away along dip from that central subfault. These correlation lengths are a function of the effective length and the effective width of our faults. This is really similar to the length and the width dimensions that we obtained earlier on, but they're just slightly different. And so combining this all together, we end up with this correlation. So we have the correlation with all of these subfaults with our central subfault. So we can see here near the center, we have a lot of these yellows and orange colors, which means that those subfaults are highly correlated, which means that they are highly likely to slip when that central subfault is slipping. However, all of these subfaults that are further away are in the blue region, which means they're not very correlated and they're less likely to slip when the central subfault is slipping. So finally, now that we have our correlation function, we can use, or we can create our slip vector using what we call the Karunin-Loew or KL expansion. Our slip vector is a vector that contains the slip on every single subfault. And we can write the KL expansion like this, where the slip on each subfault is equal to that mean slip that we calculated. And then we're summing up some terms in the summation term. Here, our lambda sub k and v sub k are these eigenvalues and eigenvectors of our correlation function. The z sub k is a random weight, so it's any number between 0 and 1. And this is just a way to add some variability into our rupture models. That way, not every single magnitude 8 earthquake with the same rupture dimensions will have the exact same fault slip pattern. This just adds that variability to it. And then these are all summed up from 1 to n. N is the number of modes. This is a number that can be any number up to the number of subfaults that you have. But the higher the number that you have, the larger the number you have, the greater the resolution you have and high frequencies, but it's more computationally expensive. So to kind of illustrate this concept of modes, I have this figure over here on the left, where this shows the first 12 modes. And so it kind of shows just like the spatial sort of distribution of slip with each mode. And in the beginning, we have sort of these like larger disparities, but as we increase in the number of modes, we get a lot more of that finer scale resolution. This is another figure sort of illustrating this, where we have the Cascadia subduction zone fault. And here, this just shows the first 5 modes of slip. So it's how the slip is just distributed for each of these modes. So yeah, ideally you would want to use a large number of modes that equals the number of subfaults that you have, but you can decrease that if you need to speed up computation time. Once we have our slip pattern, we want to determine the kinematics, or how the slip actually evolved over time. So what we want to do is calculate the rupture onset time of each subfault. This is determined using a background rupture distribution, which is essentially the rupture velocity, so how quickly slip transferred from one subfault to the next. This is the equation for that rupture velocity. It's a function of this thing called a shear wave fraction and the shear wave velocity. Our shear wave velocity comes from that velocity model that we use, and the shear wave fraction is just a parameter we can define. Usually it's 0.8 or 80%. So our rupture velocity is typically 80% of our shear wave velocity. Once we have that initial background rupture distribution, we can perturb the rupture speed a little bit. So we reduce the speed in depths approximately less than 10 kilometers in depth. And this is because we're assuming that there is an accretionary wedge in those shallow depths. And the accretionary wedge is really compliant. It's full of like really compliant loose material. And so the rupture speed will be a lot slower through these or through this type of material. And so that's why we reduce the speed. FakeQuakes has usually been used in this sort of subduction zone setting, but you can use it in other settings, and there is a way to change it to where you aren't reducing the speed at those shallow depths if you're not actually in the subduction zone. I'm going to just go over this slide and then I'll answer the question that just popped in. Once we reduce the speed in those shallow depths, we can then also perturb the onset times of each subfault so that there is faster propagation where slip is large. And then the subfault rise time, which is the amount of time it takes for one individual subfault to slip, that's scaled by the square root of the total slip. This basically means that in areas where you have larger slip, you're going to have a longer rise time. This makes sense if you think about it, because if you have one subfault that is slipping 10 meters and one subfault that only has to slip 1 meter, it's going to take longer to slip a full 10 meters. And then finally, a slip rate function is applied just to determine how that slip is evolving over time. So I'm just checking the questions real fast just to see if this next question was. Someone is asking if there's a magnitude limit for the model, would you be able to simulate really small earthquakes smaller than a magnitude 3.5, where the faults are really small, subfaults are small? I think, yes, you can generate small earthquakes. Like you said, if you are using really small subfaults, just the only difficulty would be if you're trying to generate a small earthquake, but you don't have a really small or fine scale fault model, because then you have only a couple subfaults and hardly anything is really showing up in your rupture model. But I do think that this is possible if you have a really good fine scale fault model to be able to generate smaller earthquakes. Yeah, for the rupture model parameters that you would want to define in FakeQuakes, there are a lot of them. Thankfully, a lot of them you don't really have to think about, they just have to be defined once. But I'm just going to highlight a few of the ones that you'll actually want to think about if you are generating synthetic data. So one is your UTM zone. So you'll want to define the time zone in the area that you're generating your rupture. You also want to define an epicentral time. Really, this could be any time if you're just generating random data, but if you're trying to recreate a specific earthquake scenario, then you would want to use that as your epicentral time. You also want to define a target magnitude. This could be one value, or you can have an array of values if you want to generate earthquakes for several different magnitudes. You also have hypocenter. This can be set to none if you want a random hypocenter, or you can give it the coordinates of your desired hypocenter. Next parameter is force hypocenter. It basically goes hand in hand with this other parameter. So if you want to define a hypocenter, you give it the coordinates, and then a force hypocenter has to be set to true. But if you want random, hypocenter has to be set to none, and then force hypocenter is false. It's a little confusing, but yeah. Then the rake parameter is this value that's just the average rake that you want for all of your subfaults. Then your scaling law is what determines what type of earthquake you're actually generating. So you can just put T for thrust, N for normal, or S for strike slip. And then we have this parameter called force magnitude. When we're generating the data, we give it our target magnitude, but due to the stochastic nature of these rupture models, they aren't always going to be exactly the magnitude that you give it, but it'll be close. If for some reason you're like, I need to have an earthquake scenario that has exactly this magnitude, you can set this to be true so that you're forcing it to equal your target magnitude. And then finally, there's this parameter called force area. If this is true, this forces your rupture model to fill the entire fault model that you gave it. If your fault model is pretty small and it is the area of the fault you want to rupture, you could set this to true. But usually that's not the case. Like in Cascadia, we have this really large fault model, but when we're rupturing different earthquakes, most of them are not filling the entire fault. And so we would want to leave this false so that it isn't filling our entire fault model. And then we have finally the number of modes. This was the number you can specify that can be up to the number of subfaults you have ideally, but this is something that you can change. I do have the full list of parameters in the lab that you're going to be going through, that they're already defined. And I do have little descriptions next to each parameters so that you can remember what all of these are for, but I just wanted to give you just a little introduction to what these parameters look like.
Hey, Tara, there's a question. It says, does it allow you to define several nucleation centers in order to simulate swarm quakes?
At the moment, I don't think it's been used in that way, but potentially maybe that's something that could be modified. I mean, I know that FakeQuakes is still pretty new, I guess, in the grand scheme of things. And so there are a lot of things that we're still applying and adding and expanding on. So that might be something that we could look into adding. But I think with the current design of FakeQuakes, there's only one hypocenter and just like one rupture scenario at the moment. Yeah, so that is goes over how to actually generate the rupture models. I wanted to show just a couple examples of the outputs of what FakeQuakes produces. So if you create one scenario, you'll have this .log file. This .log file is basically sort of a large scale overview of the rupture you created. So it lists your run number, the number of modes you wanted. If you look all the way down here, you can see the target magnitude. For this scenario, I wanted an 8.5. The actual magnitude of this scenario was an 8.3, so pretty close. It also gives the coordinates of that hypocenter and the time. So it's just sort of this large scale overview of what that rupture looked like. It also produces these .rupt files, which are basically, this is your rupture model. It's very similar in structure to the fault model. So you have, your subfault number, your longitude, latitude, depth, all of that. But there are a couple of columns that are added to produce these .rupt files. So we have these columns here for the subfault slip. So we have strike, slip, and dip, slip. So the amount of slip in the strike, slip, and dip, slip directions. And then we have this column for the rupture onset. So this gives you the amount of time after the rupture initiated that subfault started to rupture. So yeah. Let's see. These are some examples of what the rupture models actually look like if you plot them. I've already shown you guys this figure. This is from the Cascadia region. So this shows rupture models from several different magnitudes ranging from a little over magnitude 8 to over magnitude 9. And as you can see, as we increase in the magnitude, we're filling a lot larger fault area. But like I said before, FakeQuakes can also be used to recreate a certain earthquake scenario if you already have a fault model to go off of. For example, in this scenario, this is from some of my work. So I have a fault model here, which is my mean slip model. This is for the 2010 Mentawai earthquake. And then these two panels are just some FakeQuakes perturbations on that mean slip model. And then another example of this is here from the Skoldberg paper, where they were recreating this the Iquique, Chile earthquake. Right here, this is their mean slip model, or the fault model that they're going off of. And then these are some of those stochastic simulations that they created using FakeQuakes.
Hey, Tara, there's a question in the chat. Says, what are the criteria to select the source time function?
Yeah, FakeQuakes has, I think, 3 sort of defaults you can choose from. There's a Draeger source time function, a cosine, and a triangle. I think there is an option or a parameter you can set if for some reason you have your own custom source time function that you could input. But usually I think people use the Draeger source time function, but there are a couple that you can choose from. And that's just one of the parameters you can define in the parameter file. After we generate our rupture models, we can actually start generating the waveforms. So we start out with our low frequency waveforms, which are displacement at first. These are created deterministically. This means it's based off of the physics of how waves propagate through a media. So it uses that 1D velocity model and Green's functions. Green's functions are what the seismogram would look like for 1 meter of displacement, assuming a delta source time function. The delta source is basically this infinite instantaneous impulse. And then these Green's functions are calculated assuming a layered half-space model, and then using this thing that we call a propagator matrix. This propagator matrix is basically a mathematical way of getting from the amount of slip that you have on your fault to the displacement that you see at the surface. So it's relating that rupture or the slip on the rupture to creating your actual waveform. This propagator matrix has a lot of different parameters, but basically it depends on the depth and the velocity, both the shear wave and the P wave velocity, as well as the rigidity. So yeah, this is mathematically kind of what that looks like. And we create these Green's functions first for every subfault station pair. So we are kind of assuming each subfault is its own individual source. like I said before, these Green's functions are kind of simplistic. They assume only 1 meter displacement and they assume this delta source. But realistically, we know that the rupture is rupturing more than 1 meter, or it's not always just rupturing 1 meter. And the source does not look like this sort of instantaneous source. And so FakeQuakes then creates this product called a synthetic, which kind of gives a better idea of how that displacement actually evolved over time. We get these synthetics by convolving our Green's function with a source time function. So we have our Green's function, and then we can define a source time function. Like I just mentioned, there's a Draeger, a triangle, or a cosine source time function. And once we convolve that, we get these synthetics. And again, we have these synthetics for each subfault station pair. We then scale these synthetics by the amount of slip on the subfault. So if you remember from that rupture model or the rupture file that FakeQuakes creates, we have those columns for the amount of slip on the subfault. And so we scale these synthetics by that slip from the rupture file. So visually, this is kind of what this looks like. This blue triangle would represent one station, and this would be our fault model. And then every subfault is contributing its own little seismogram at first. But then we can sum all of our subfault seismograms together, and this gives us our final displacement waveform for one station. There are only a couple parameters we really need to think about for the low frequency waveform part. The first is the sampling interval, which is the amount of time between each sample. And then this thing called NFFT. It is the number of samples in your waveform, and it has to be in powers of 2. For some reason, that computation time, it just needs to be in this powers of 2 form. So for example, if you want to create a low frequency waveform that has a sampling rate of 2 Hertz, the inverse of that, or the sampling interval, would be half a second. Oops. And then let's just say you want 512 points in your waveform. You can multiply that dt by the NFFT, and that gives you the duration of your entire waveform, which for this scenario would be a 256-second waveform. This is just an example of what these low frequency waveforms look like. So this was just a really coarse rupture model that I created for magnitude 8.5 event. This is in the Mentawai region, and using this rupture model, I created these 2 low frequency waveforms for 2 different stations. Here, this PPSI station was located a lot closer to the rupture. And so you can see here that the displacement has this static offset. The displacement doesn't go back to 0, and that is because the station is so close to the rupture that there's some amount of permanent deformation. This MNSI station was located further away, and so we can see that the displacement at the end of the rupture returns nearly to 0, and so there's not much static offset or permanent deformation here. After we generate the low frequency waveforms, we can create those high frequency waveforms. These are created stochastically, which means there's a bit of a random aspect to it. This is done very similarly to that stochastic high frequency simulation method that I mentioned at the very beginning, that people used to use on its own for creating synthetic data. The reason that we do this stochastically is because high frequencies are just really computationally expensive to generate. It's also difficult to resolve the finer features of the subsurface at these high frequencies. So the low frequencies were done deterministically, and so they used a velocity model. And the velocity model that I have is a really coarse velocity model. There's not a lot of fine scale detail in it, which is fine if we have low frequencies such as this, which has long wavelengths. But if we have high frequency data, we would really need a really detailed velocity model to be able to resolve all these high frequencies. And in many regions, we don't really have a velocity model that's that detailed. And so it would be difficult to create these deterministically. It's not impossible, but it's just not really realistic in most scenarios. So to create these acceleration waveforms, we are creating these in spectral domain. So we're creating an amplitude spectrum for each subfault. And we do this using this equation here, which has different components of the ground motion, kind of like that equation from the beginning. So here, we're creating this amplitude spectrum, and this first term is this radiation scale factor. You don't really need to know too much about it, but if you're interested, it has parameters such as this free surface amplification, the radiation pattern, shear wave velocity, density, things like that. Then we have our source spectrum. We are creating acceleration for this part of the waveform generation, and this is what the acceleration spectrum should look like for source. And so there are a couple parameters within this part of the equation. This m is sort of the individual subfault's magnitude, so its contribution to the entire magnitude. There's also corner frequency, a couple parameters like that. Then we have the path effects. If you remember, as the waves propagate out, they start to attenuate. This is due to different types of attenuation, such as like geometric spreading. As your waves are propagating away from the source, they're spreading out over, or the energy is being spread out over a larger area. And so you have a decrease in energy density. There's also attenuation as these waves are, or as the energy is being absorbed or transformed into heat. And so this term basically accounts for all that sort of attenuation as the waves are propagating through the path. And then finally, we have this other term, which gives our decay of those high frequencies. This is more of a site parameter. So we have this exponential term, which has kappa. This is that kappa from the station file. So if you have station-specific kappa values, you can use that here, or you can just use the default average value. And that describes that high frequency decay you see from different type of attenuation from site conditions. And so when we combine all of these aspects of the spectrum together, we end up with our full acceleration spectrum. We then combine this with the phase of random white Gaussian noise. And again, this is done for every subfault station pair, kind of like we did with the low frequency waveforms. This is all still in the spectral domain. But once we have all of this, we can inverse Fourier transform and turn this into the time domain so that we end up with these waveforms for each subfault. And then we can sum these all together just like we did with the low frequencies, and we end up with our one acceleration waveform for the one station. And I think someone else just asked a question. Is any rupture radiation pattern accounted for when calculating the waveforms for distributed stations? I'm not exactly sure this is asking. I think, are you asking if you can have different radiation patterns, or I'm not 100% sure what they're asking, but I think FakeQuakes has a radiation, like a default radiation pattern that it uses in its equation. If that didn't answer your question, you can, I guess, ask me again in a minute with, yeah, if you're still confused by that. The parameters that we need for the high frequency part include this thing called the stress parameter. This is the stress drop, so the amount of stress that's released during the earthquake. This parameter is measured in bars, so a standard value is 50 bars, which is the same as about 5 megapascals. We also have the depth to the MOHO. This is something you could look up for the region that you're working in. Then we have this P-wave parameter. This is a true or false parameter, and so if it's true, you are modeling P-waves in your data. The kappa was that kappa value that describes that decay in the high frequencies. A standard value is 0.04 seconds, so that could just be the default for all the stations. And then we have the sampling interval for the high frequency component. And then finally, we have this duration, which is the length of the waveform that you want. This ideally would be something very similar to the duration that you would have for the low frequency waveforms, but it doesn't have to be exactly the same. And here's an example using that same rupture model that I had created for that magnitude 8.5 event. These are the same two stations that we looked at before, but this is just the high frequency acceleration part. And then let's see, okay. The question is just, I think someone's asking about the directionality. Let's see. The directionality of the fault with respect to the stations. Sorry, let me think about this for just a second. Is any rupture radiation pattern accounted for? And you're asking about the directionality of the fault. I think I think it doesn't really matter where the stations are located with respect to the fault. Yeah, I think they can really be located anywhere. I don't think that really matters too much, but I haven't really tested it for a lot of different scenarios. Finally, once we have our low frequency and high frequency waveforms, we can create our broadband waveforms. This is a pretty fast part of the process. There are a couple things that have to happen though. If you remember, our low frequencies are in displacement and our high frequencies are in acceleration. So our low frequency waveforms have to be double differentiated so that they are transformed into acceleration. Then our two waveforms are currently have different sampling rates. And so the low frequency waveforms are then resampled so that they have the same sampling rate as the high frequency waveforms. After that, the low frequencies and high frequency waveforms are trimmed so that they have the same length. Then our low frequency waveforms are low pass filtered so that we are mainly retaining the low frequencies, and the high frequency waveforms are high pass filtered to retain the high frequencies. And then finally, these two waveforms that have been filtered are summed together to get our final broadband waveforms. I have a figure here that kind of just illustrates this process where we have in this first panel, our high frequency waveform is in blue and the purple is our low frequencies. And this is after they're already both acceleration. Then they are low pass and high pass filtered. And that gives us our second panel here. And then finally, these are summed together to give us our broadband waveform. There's not a huge obvious difference after filtering when we're looking in the time domain, but if we look at this in the frequency domain, you can see a little bit more what's going on. So here in this first panel, this is the acceleration spectra for high frequency in blue and our low frequencies in purple. And then after filtering these, we get the purple and blue on this side. And then those are added together to give our spectra, our broadband spectra, which is in orange. There are a couple parameters that we can define or change for this part of the process. And this is called a matched filter process. And here we have this thing called the zero phase. This is either true or false. And if it's true, you're filtering twice to remove a phase shift. If you're familiar with signal processing techniques. We have this other thing called the order, which is the filter order or the number of poles. If you look over here at this figure, these top panels show the filter response of 3 different scenarios. So we have a 2-pole filter, a 4-pole filter, and a 6-pole. If you look at the 2-pole filter, the roll-off of this filter is a little bit more gradual, but as we increase to 6 poles, it's a lot steeper. And then these bottom panels down here just show the spectra for different events using these different filter responses. And so you can see using different number of poles can slightly affect what your spectra actually look like. Increasing the number of poles added this sort of large dip in our spectra. So this is something you could maybe mess around with if you're really interested in the signal processing part of this. But generally, I think someone would use around 2 or 4 poles. There's also this thing called the corner frequency. So this is the frequency where your filter is starting or stopping. So here we have an example of changing the corner frequency to see how that would affect our spectra. There's kind of a lot going on in this figure, but if you focus just on the dashed green line, this is where we had our corner frequency. So in this top panel, this corner frequency is really close to 1 hertz. But then as we go through the panels, we decreased our corner frequency all the way down to 0.1 hertz. And if you look closely in this top panel with the larger corner frequency, there's kind of this bump or this dip in the spectra. But when we decrease our corner frequency down to 1 hertz, it was a bit smoother. So this is something you can also mess around with if you want. But I think typically people do use a value close to 1 hertz. And so this is our final example for this scenario where we have, again, our 8.5 magnitude earthquake rupture scenario. And then these are the same 2 stations, but with the broadband waveforms. So this was the low frequency and high frequency combined. So in summary, using FakeQuakes, we can generate these rupture models, and it uses a von Karman correlation function and a KL expansion to produce the slip patterns. Then we create these low frequency waveforms deterministically using our velocity model and Green's functions. Then our high frequency waveforms are created stochastically. This is done in the spectral domain. And then we inverse Fourier transform to get our actual waveforms. Then finally, we combine both of these waveforms to get our final broadband waveforms or our final products. So I think now we're going to take a break, but it will be your turn. And I do have a lab that you can walk through. Before you start the lab, I want to make sure that you guys have set up your startup script. So whether you're modifying your bash profile or bash RC, whatever script you're using, we want to make sure that that is set up and that you have MudPy installed. And then we're going to be working through this thing called the Roses FakeQuakes lab. It's the one from the FakeQuakes tutorial repository, not the one in the Roses 2021 repository if you have that. And then make sure you've done a git pull in this FakeQuakes tutorial folder just to make sure you have the updated version of everything. You guys will be generating data for a couple different earthquake scenarios in the Mentawai, Indonesia region. And so I've already given you guys the 3 input files that you need. And these are located in the files folder within FakeQuakes tutorial. And yeah, so we'll give you, I guess, guys, time to take a little break and to make sure everything is set up. And if you run into any problems, let me know.
Yeah, let's take about a 10-minute break. Tara, do you want to stop sharing your screen for a second, and I will put up a timer so we're all on the same page.
I did notice someone asked one other question real fast, where they asked if there is a value kind of where something's considered low frequency or high frequency. And usually this is about 1 hertz. So we generally say the low frequencies are everything less than 1 hertz, and the high frequency is stuff above 1 hertz.
Cool, okay. So we'll do a 10-minute break, and then we'll come back and we'll start working through the lab here. Our timer. Okay, and we'll see you back here in 10 minutes.
Hey, Francisca, we're seeing your paper, not the timer, just so you know.
Okay, that was our 10 minutes. I think if folks are back, we can go ahead and get into the lab section.
Okay, I was going to pull up, see my version of this lab. Can you guys see that? Cool. I'm just going to walk you through just kind of getting the first part of this exercise down. All 3 exercises are pretty similar. It's just changing a few parameters. FakeQuakes has a lot going on behind the scenes, but the amount of work you have to do is actually not that much, mainly just defining those parameters. So yeah, we'll just kind of go over how to do that using this lab. I gave just like a quick overview of FakeQuakes if you wanted to read through that here. I linked a few things for other, just other information. Yeah, other information. Some of this stuff from FakeQuakes is outlined in this paper by Diego Melgar, which I've linked here. I also have some information on my GitHub where I have like a wiki page also explaining how to set up all these parameters if you wanted to know some more. I included this information on the project setup just in case for some reason you haven't had a chance to do that yet. But if you have, you can just scroll through all of this. One thing you might need to do is if you've edited your .bash profile or your bash RC script, you might have to reload it so that it actually notices those changes by typing source.bash profile into your terminal. Yeah, so if you end up running into any issues that's like MudPy doesn't exist, then it's just not seeing the path that you put in there. So you'll just have to reload that script by typing this. Before you generate synthetic data, we have to create a project folder. And this project folder creates a lot of subdirectories where it actually stores all of the information. So it stores your Rupture files, greens functions, waveforms, everything like that. And so FakeQuakes has a function that initializes all of this. So mainly we just have to define the path to where we want this to be located. Also, when we create a new project folder, we would want to do this every time we have a new set of parameters. So as you go through these couple exercises, we'll create a new project folder for each exercise. There are also 3 files that you need for generating the data. We have our velocity model, which I have for the Mentai region. We have our fault model, which is a little bit of a coarser fault model, just to kind of speed up some computation time for you guys going through the lab. And then I have this sm.gflist. This is our station file. SM just stands for strong motion because we're using strong motion stations. And this only has 2 stations in it. But if you're generating your own data, you could create your own station file that has as many stations as you want. So to get started, you would want to go ahead and run this first cell, which imports everything. I included this little line to install Numba. If you're using the Roses Conda environment, for some reason, it just doesn't have this, which is already usually included with Anaconda. But yeah, you can go ahead and run that. This next cell includes all of the parameters that we need. So there are a lot of parameters to run the different aspects of FakeQuakes, but you don't need to worry about a lot of them. There are only a couple that you'll actually be changing for the different exercises. But if you did want to know more about what each of them does, I included these little descriptions over here on the side just to explain it a little bit better if you're confused as to what they do. But make sure you do actually run this cell because you need all these parameters defined. So once you do that, the first exercise is just to generate 2 rupture models for a thrust earthquake with a target magnitude of 8.5. And for this scenario, we'll just set the hypocenter to be a random subfault. So the first thing we do is creating our project folder, like I mentioned. You can run this cell. You want to change this to be the name of the project folder you want. So for me, I might name it Lab 1. Home is already defined to be your current working directory, but if you don't want that, you can change this to be the path to wherever you actually want to save your project. And so the path to home / your project name is where all of your directories will be stored. Once you run this, then you can run the next cell, which will actually initialize everything. And hopefully it should work and it won't give you any errors. Once you initialize your project folder, you would want to move your velocity model or fault model and your station file into their certain directories so that when you're running FakeQuakes, it knows where to actually find these files. I listed where these files actually go here but if you run this next cell, this will automatically copy everything over for you if you're working within that FakeQuakes tutorial folder. The next thing that you guys will want to do on your own is change the parameters that you need. I realized one thing I didn't mention was this N realizations. This is the number determining how many synthetic rupture models you're creating. So for this exercise, I mentioned generating 2 rupture models. And so in this case, N realizations would be equal to 2. Our target magnitude is the magnitude that we want to generate. It has to be an array, whether you're doing one magnitude or several. So for this case, I believe I mentioned in magnitude 8.5. So you can type 8.5 there. The hypocenter would be set to none, or you can give a list which has a longitude, latitude, and depth. For this exercise, we just wanted a random hypocenter, so you can just set that equal to none. And then because this is equal to none, we don't want to force our hypocenter, so this has to be false. For this scenario, we are generating a thrust earthquake, and so this would be a T for thrust. And finally, force magnitude. This is up to you. If you want to test setting this to true and having it generate an earthquake exactly equal to a magnitude 8.5, you can, or you can set it to false. That's just your decision, however you want to have your magnitude. You want to define all these parameters, and then if you run the next cell, this will actually start generating your rupture models. It uses this function called generate ruptures that's within the FakeQuakes script within MudPy. And this should take probably less than a minute. It won't take too long to generate. If you guys do run into more errors with this or have questions, you can send that through the chat. Also, if you when we're running this in FakeQuakes, it doesn't always output everything that's going on here. But if you open up your terminal, it should show the print statements kind of showing how far along you are in the rupture model generation or generating the FakeQuakes. It should be doing a lot of print statements. So if you're interested, you could look at your terminal to see what it's saying. Okay, mine stopped running, so I'll show you what my rupture models look like. Hopefully yours was working okay too. So FakeQuakes has this thing or this function called view.quickModel. So it just shows sort of a coarse plot of what your rupture model looks like. These rupture models are located in home, project name, output, and then ruptures. So all of the .rupt and .log files are located in this output ruptures directory. So we can run this. And for me, these are what my 2 rupture models look like. I don't know why in a notebook it makes these all kind of squished and weird. This is one of my magnitude 8.5 rupture models. And then this is my other one. And as you can see here, FakeQuakes has this variability. They both have the same magnitude. But this one is skinnier and longer. And this one down here was a bit more of a, I guess, a fatter rectangle. So you can see some differences in the types of rupture models that FakeQuakes can create. If you run this next cell, this will show you what that what one of those .log files looks like. This one's showing just that first rupture, which is ends in a 0. I think I forgot to mention this, but all the ruptures are numbered, and so I set sort of the base name of our ruptures to be men to y because we're working in men to y. That was one of the parameters. And then they're numbered starting at 0, and they can go all the way up to however many ruptures you're creating. So this one is just that first rupture scenario. We're looking here. The actual magnitude that it created was about 8.6, but the target I defined was an 8.5. And if I change this, I can change this to be that second log file. And for that second rupture, the target or the actual magnitude that it created was close to 8.8. So it was actually a good bit larger. But yeah, if you set this, your force magnitude equal to true, then this actual magnitude should also say 8.5. So that shows the rupture models. The next part is computing the Green's functions. This takes the longest amount of time. So it'll probably run for about 9 to 10 minutes. Here I've changed this value called n CPUs. I also didn't mention what this is. This is the number of cores of the CPUs that you're using on your machine, because this is designed to be run in parallel. I started at the number 2 because I only wanted to generate 2 rupture scenarios. If I increased it, it would start creating extra rupture scenarios I didn't want. But to actually compute the Green's functions, I changed this to run on 4. And I think a typical Mac will have at least 4. If on your machine you don't have 4, you can change that to a smaller number. And then, yeah, you can go ahead and start running this, and this will take just a minute. And I think someone has already run into an error. If you want, whoever sent this error message, you can send a screenshot of the error or put that through Slack maybe, so I can see what that actually looks like. Maybe I can figure out what's going on with that. Okay, my greens functions finished running, and I know some of you are still having some issues, mostly all with the compiling part, which I know is a problem often with getting that working. So I'll still try to help troubleshoot you guys in just a minute, but I'll keep going with some of the lab just to keep getting that moving along. But mine finished running with the greens functions, and so now it's going to make the low frequency waveforms when I run the next cell. And this is a pretty fast thing to run. And these waveforms that FakeQuakes creates, they're located in the output folder. The ruptures are in output ruptures, and the waveforms are in output waveforms, which makes sense. Oops, it just started scrolling. Here we go. The low frequency waveforms have this channel code that starts with an LY. So it'd be LY, an LYE, LYN, or LYZ, or whichever component you're working with. And this next cell will plot what some of those look like. Here I have it just plotting the east component. And I'm just using the opti trace plot function. But if you wanted to use matplotlib, you could do that as well. It's kind of up to you. But this is what my low frequency waveforms look like for my two stations. And then, let's see if we keep scrolling down, we can start working on the high frequency waveform part and run this cell. This takes a little bit of time, not nearly as long as a greens functions computation, but it'll take about 4 or 5 minutes. So while that's running, I'll try and see all of your messages to see where people are getting stuck. Okay, hopefully we're getting some of these kinks worked out. Oops. Thank you for those of you who have already found some of these errors and have been able to find solutions, because there's so many problems that can come up and I've only come across some of them. So it's nice that other people are able to find solutions to these problems. But in the interest of time, I'm going to keep going through this part of the notebook just so you can guys see what this looks like. So this has finished running the high frequency parts. There's a cell just plotting that so you can quickly see what those look like. Again, I'm just plotting each component on both of these stations. These are also located in the project name output waveforms folder. And these are identified by having an HN star code. So like hne.mpi, not the ones with the BB, that's for broadband, which I will also explain in the broadband part. After generating the high frequency part, the last step is really fast. It's that matched filter process that combines the low frequencies and the high frequencies. So when you run that cell, it's pretty instantaneous. And then now you should have all of your waveforms. The broadband ones are indicated by the bb.hn for broadband. And if you run the next cell, you can go ahead and see what those look like plotted up. And then that is basically it. Once you get through this first exercise and you're able to get everything running, the next two are pretty straightforward. It's the same exact thing. You would just change a couple parameters such as the magnitude. So yeah, hopefully we're working through it with you guys. But if you do still run into problems, keep messaging us and we'll try to figure out how to get that fixed. I'm going to go ahead and just stop sharing my screen. But if you guys need me to show anything, just let me know.
Okay, thank you so much, Tara. I think we will end our unit for today. Feel free to continue to use the Slack and hopefully we can do some group troubleshooting as you all work your way through the lab. And we will see you back here next week.